Welcome to the fourth webinar organized by the SAES Vacuum Technology Division. Today we are going to talk about an essential tool for vacuum technology, which is the residual gas analyzer. We will present the basics of quadruple mass spectrometry. Then we will discuss about the spectra and their interpretation. And we will conclude with a couple of interesting examples that have something to do with the use of NEG pumps. Let's start with some basic concept about quadruple mass spectrometers. First of all, why mass spectrometry? In some way, our vacuum system is like this present. A gauge tells me about pressure, but then we want to know what's inside. Our goal is to get a picture of the composition of a gas mixture, either qualitative or quantitative, depending on the application. Frequently, we are interested in the background atmosphere of a vacuum chamber, so we speak about residual gas analysis, and the instrument is often called a residual gas analyzer. With an RGA, we can evaluate gas sources and search for contaminations, assess the cleanliness of a component, drive a bake process, perform leak detection, study the outgassing of materials, assess the purity of a gas bottle, or monitor processes as, for example, plasmas and thin film deposition. We can say that mass spectrometry is a key technique for almost every vacuum technology study. How does a mass spectrometer work? We have three main components that carry out three fundamental tasks. The ion source creates ions. The filter separates them according to their mass-to-charge ratio. And the detector counts them, delivering a current signal. The partial pressure is proportional to the ion current of a reference ion for each gas species. The factor is called sensitivity, and it is calibrated for each gas of interest. Let's say something more about each of the three components. Commonly for vacuum technology applications, the ion source is an electron impact ionization source. Because it is rather cheap, it is very stable and reproducible. A filament emits electrons via thermoionic effect. The filament can be made of tungsten, rhenium, or yttrium oxide-coated iridium, depending on the application needs. Electrons are accelerated and collide with the gas molecules. Electron impact ionization is a threshold process. Electron energy must exceed the first ionization energy of the molecules. Typically, an electron energy of 1790 eV is okay for the species of interest. Then, ions are extracted and focused by proper electrodes and injected into the mass filter. The main features of our source are ionization efficiency, the interval of linearity, that is, the pressure range within which the number of ions is proportional to the pressure. Indeed, there's a pressure upper limit above which there is the onset of space charge effects that cause a deviation of the sensitivity. Then, the outgassing can be very important, since it affects the detection limit of the instrument. In ultra and extra high vacuum, low outgassing sources are used, in which the bulky electrodes are replaced by narrow grids. There are many kinds of filters, but the most used for residual gas analysis is by far the quadruple mass filter. It is made of 4 cylindrical bars, and opposite bars have opposite polarity. The applied field has a DC component U plus an oscillating one V at a frequency in the MHz range. The field does not affect the motion along the rod axis Z, but on the XY plane. The particles with a stable trajectory can reach the detector, while If the trajectory is unstable, the ions are lost on the electrodes. Acting on U and V potential, it is possible to select a narrow transmission window for the given mass-to-charge ratio, so that we can focus on a specific ion or perform a scan of the whole mass range. As to detectors, there are basically two families: the Faraday cup and the secondary electron multipliers. They differ in sensitivity or gain, detection speed, signal-to-noise ratio, and clearly price. The Faraday cup collects the charge carried by ions, and the signal is converted into a voltage by means of an electrometer amplifier. It is simple and robust. It has a good long-term stability, and it is compatible with high-temperature bakeout. However, its gain is not large enough for use in UHV, and it is not good for fast measurements. Secondary electromultipliers have one or more diodes under high voltage, 1 or 2 kV, covered with low work function coatings. The incoming ion causes an avalanche, and at the end we collect a current. These detectors have a very high gain, so they are suitable for very low partial pressure typical of UHV. They are very fast and have much higher signal-to-noise ratio with respect to a Faraday cup. On the other hand, they are more delicate. The gain gradually decreases with time, and we have to increase the voltage. And they are sensitive to air exposure. They cannot be used at pressure higher than 10 to the minus 5 millibar, and their cost is much higher than a Faraday cup. Let's see where the signals of a mass spectrum come from. There are basically three phenomena to take into account. The first is fragmentation. The ionization can break chemical bonds, so that a single molecule can give origin to several different fragments. This is particularly true for large molecules like hydrocarbons. Then, a molecule or a fragment can be ionized 2 times. Such ions will have apparently half mass in the spectrum. Finally, atoms have isotopes. For example, carbon has 3 naturally occurring isotopes, which can take part in the formation of molecules, so that we have CO made up by C12 or C13, with molecular mass 28 or 29. So, we have seen that the same molecule can generate a lot of signals. We find all of them in the fragmentation pattern, which is a list of the signals generated by a molecule in certain conditions, for example, ionization by electron impact at 90 eV. The main peak is set as 100%, and the other peaks are expressed in relative percentage. As you can imagine, this is an essential information to interpret the spectra, and it is object of a frequent calibration if we want to make a quantitative analysis with our QMS. Here you can see that carbon dioxide, which may be considered as a simple molecule, generates quite a lot of signals, since all the 3 effects are present. Fragmentation, from CO2 we have carbon, CO or oxygen. Multiple ionization, you can see that in the list CO2 can have double charge. And there are isotopes too, of both carbon and oxygen. Considering that in a vacuum chamber there are a lot of gaseous species, the result is something like that. Commonly in a vacuum system we can find hydrogen, water, methane, CO, CO2, small hydrocarbons, noble gases. So, to interpret the spectrum in a qualitative way, we need at least the typical fragmentation patterns. While to perform a quantitative analysis, we have to calibrate our QMS to obtain precise patterns and sensitivity. Then, with the opportune algorithms, it is possible to disentangle the spectrum and get the partial pressures. Let's see what's inside a spectrum and how to recognize the different species. Everyday practice of vacuum users is mostly made of qualitative analysis. Usually, the main purposes are checking if the system is clean, if it is tight, or searching for the outgassing sources. Let's first collect the spectrum. First, we choose the mass range. If you are not interested in large hydrocarbons, 100 is enough. Then, depending on the pressure, we use the Faraday or the SEM detectors. Clearly, in UHV, the electron multiplier is required. Then, take your time to acquire a good spectrum. Let's say 0.5 or 1 second per atomic mass unit, because going too fast is not a good choice, unless you have to follow fast events. Once that we have the spectrum on the screen, where do we start? We start from expectations, that is, from the knowledge of our application. Did we meet the pressure target? Is the system baked? What are the expected outgassing sources? Or are we aware of any particular outgassing source? Looking at the data, is there something unexpected, both in the signals and their relative intensity? If the answer is yes, we can start thinking if something unwanted happened, like leaks, contamination of different nature, the most frequent are hydrocarbons, or maybe some artifact. Let's briefly recall the patterns of the main species to look for. We have hydrogen and water, then nitrogen, CO, whose main peak is the same as nitrogen, then methane, with its characteristic triplet 16, 15 and 14. Then we have CO2 and small hydrocarbons, which contribute in the range 26, 30, then with growing mass between 36 and 45, like ethane, ethylene and propane. Peaks at 15, 28, 27, 39, 41, 33 are indication of small hydrocarbons, and there are also fragments of larger hydrocarbons. Note that many species contribute to 28, so quite often it is not so easy to discern all the contributions to this peak. Let's see what we can find in a mass spectrum step by step. We divide the mass range in 5 parts, and we take as example a high vacuum spectrum showing water and hydrocarbons. First part, 1 to 10 atomic mass units. Obviously, we find hydrogen, then we have helium, and the multiple ionization of carbon, nitrogen and oxygen at masses 6, 7 and 8. Nitrogen++ is about 0.2% of mass 28, and quite a lot of nitrogen must be present to see it. O++ comes from carbon oxides, water and oxygen. In general, these peaks are strong indications of possible leaks. Second part, 12 to 22 atomic mass units. Mass 12 stands out in the spectrum when there's much carbon due to hydrocarbons or CO or CO2. The group of methane is important to understand the spectrum. The main peak is 16, which has contributions also from CO, CO2, and a little from water, which anyway must be considered if water is abundant. So, to estimate methane, it's better to look at mass 15, even if when there are many hydrocarbons, there's a large amount of methyl groups, CH3, produced by fragmentation. Mass 14 is important to understand if there is nitrogen. We have to evaluate the methane contribution to this mass and subtract it. In general, if 14 to 15 ratio is lower than 4, you should consider the possibility that a leak is present. Mass 18 is clearly the water main peak, while 19 is mainly due to H3O+, which is 0.1% of 18. 19 can contain also fluorine, which anyway may be due to an artifact, as we will see later. Then we have 20, which is the mass of neon and argon++, while mass 22 is likely CO2++ or an isotope of neon. Third part, 24, 32 atomic mass units. Mass 32 is likely oxygen, since CO2 does not produce significant fragments with this mass. So pay attention to leaks when it stands out. Mass 28 is a real puzzle in the spectrum. It receives contribution from many species, so we need to analyze other signals to understand what's inside this peak. To evaluate nitrogen, we look at 14 and 7. As to small hydrocarbons, we look at 26, 27, 29, 30, that create the typical pattern looking like a hand. CO2 is estimated by mass 44, as shown in the next slide. Methanol and ethanol have a major fragment with mass 31, so if we cleaned something with these solvents, we may see this peak. Fourth group, 36 to 45 atomic mass units. Mass 44 is CO2. It is one of the reference points that you can assume. Mass 40 is argon, but some hydrocarbon may contribute depending on their amount. The rest is mainly hydrocarbons. Typically 39, 41 and 43 stand out. Without leaks and hydrocarbons in this region you will see almost only CO2. Let's come to the difficult stuff. The fifth part of the spectrum is the one above 45 atomic mass units. Basically, we are talking about hydrocarbons with at least 4 carbon atoms. Indeed, when one has to fix a criterion to assess the cleanliness of a vacuum components, it is usually required that signals above 35 are below a certain threshold. Large hydrocarbons produce complex patterns, so it is possible to identify a species only when it is dominant. That is, the peaks clearly stand out. Anyway, it is useful to keep in mind some cases that occur quite frequently. Lubricants or pump oils are of different types. They may contain saturated straight chains, which have fragmentation groups at intervals of 14 atomic mass units, depending on the number of carbon atoms. Typically, masses like 39, 41, 43, 55, 57, 67, 69, 91 stand out in the spectrum. Aromatic compounds show the peaks of benzene 77, 78 and 50, 51, 52. Silicone oils and siloxanes typically present these peaks too. Let's see how a typical UHV spectrum looks like. This is the spectrum we collected during last webinar at about 1 to the minus 9 torr. Typically, the residual atmosphere of clean vacuum chambers is characterized by hydrogen, water, methane, CO, CO2. Water dominates unbaked system, while hydrogen is the main gas in UHV. It is not so easy to get completely rid of small hydrocarbons. What can we say about this spectrum? Water is a bit higher than expected. Likely it is mainly released by the QMS surroundings. Indeed, the pressure was 10 to the minus 10 torr before switching on the QMS. We see methane as expected. Nitrogen presence is unlikely, so 28 is mostly carbon oxides and small hydrocarbons, as we can see 27, 26. Then we have CO2, which is expected to be there. When the pressure is lower, below 10 to the minus 10 millibar, we speak about extra high vacuum. This spectrum was collected in our lab at a very low pressure in the low minus 11 millibar range. In these conditions, carbon-containing species dominate besides hydrogen. Water is much lower than in the previous spectrum, and we have methane, CO2, and small hydrocarbons. Their presence is confirmed by peaks at 26, 27, 39, 41. Contribution on peak 12 confirms the predominant role of carbon species. Please note a peculiarity of this spectrum. Usually in XHV, hydrogen is by far more dominant in the spectrum, but this system was provided with a lot of getter pumping speed that lowered hydrogen partial pressure. In a system pumped by turbomolecular pump or a sputter ion pump, the contribution to the total pressure is typically much higher. So everything seems clear, but actually there is something that makes little sense. In a CH4 pattern, mass 15 is about 86% of 16. Here it is 16%. In a water pattern, mass 19 is 0.1% of 18. Here it is almost 20%. It seems we have unexpected contributions on 16 and 19. Indeed, they are artifacts that can be found at very low pressure, and they come from electron-stimulated desorption. Let's talk about some artifacts that can occur in QMS spectra. The first is typical of very low pressures, below 10 to the minus 10 millibar, and has to do with the electron-stimulated desorption occurring in the ion source. The point is that ions desorbed from surfaces after electron impact have higher energy than other ions, and they can reach the filter more easily. It is possible to vary the focus parameters until other ions coming from the background gases disappear, as you can see in the example. In this way, you can distinguish these artifacts. The second kind of artifacts is mainly related to high vacuum systems where water is present. All filaments work at high temperature, and the chemical reactions occur at their surface, depending on temperature and their chemical nature. In particular, all filaments produce CO and CO2 in presence of water, and tungsten produces methane too. So pay attention when a lot of water is present. For example, try to see if carbon oxides and methane signals follow the water evolution in the chamber, and take into account that dirty filaments, which for example have been in contact with hydrocarbons, will always produce some excess CO and CO2. The third artifacts have to do with the first mass of the spectrum. At very small or zero potential of the filter, ions that should have unstable trajectory may be transmitted. This causes an apparent higher signal at the beginning of the scan called zero blast. This effect is suppressed by preventing the voltage from reaching small values below mass 2. The message is: do not care too much about mass 1, it may be not reliable. What about leaks? How to recognize them? Leaks can occur for many reasons, like actual leaks, so from the external atmosphere, or virtual leaks, that is air trapped somewhere in recesses of the chamber, like bad welding, screws, or porous material. In particular, the latter should be absolutely avoided in UHV. The problem with virtual leaks is that there is a small conductance between the air volume and the pumps, so it takes really a lot to empty them. Then air can leak into the vacuum system due to permeation from elastomer sealing. Large leaks are easy to identify. We have a huge 28 and 32 peaks of nitrogen and oxygen, a large 30 from argon. 14 is higher than 15, and this is always an indication of nitrogen presence. Then you can see multiple ionization peaks of nitrogen and oxygen at mass 7 and 8. When leaks are smaller, it is not always easy to assess their presence in the spectrum. For example, this spectrum has been collected in a high vacuum system. There's a lot of water and hydrocarbons too. Mass 7 is not distinguishable from the background. 8 is present, but there's a lot of CO2 that can account for it. Mass 32 suggests a possible leak. Mass 40 is compatible with the hydrocarbon amount. It may be C3H4. Let's analyze mass 14. The question is, does methane account for all the signal, or is there some nitrogen? In the spectrum we have a certain current of mass 14 and 15. We know that in the pattern of methane, mass 14 is 14% and mass 15 is 86% of 16. With a simple calculation starting from the current of mass 15, we can derive methane contribution to mass 14, which is only 25% of the signal. So methane is responsible for 25% of the signal, and we can conclude that nitrogen is likely present. Please note that mass 15 may be overestimated due to hydrocarbon contribution, so our calculation is conservative. It would have been quite impossible to extract any information about nitrogen from peak 28. In general, try to start the analysis of the spectrum from peaks that have a main contribution from one species only. Now we show two interesting things about NEG pumped systems. We show a couple of examples of mass spectra acquired in a system with an NEG pump. In these experiments, the QMS allows us to understand what's really happening, showing the benefits of using an NEG pump. You have seen that one of the key advantages of non-evaporable getters is the ability to pump without any power source. So it is interesting to see what happens in a system with a NEG pump when there is a power outage. We consider again the setup used in the last webinar, equipped with the Nextor Z500 combination pump. Turbomolecular pump is isolated and we turn off the ion pump. As soon as the ion pump is turned off, we see that some signals rise. This is due to the fact that the getter cannot pump noble gases and methane. Indeed, the only signals rising are 14, 15 and 16 corresponding to methane. Mass 40 of argon does not change since the system is really leak tight. Pressure soon stabilizes, and no signal from getterable gases like water, CO and CO2 changes significantly, since the pumping speed of the getter cartridge is by far higher than the one of the ion pump. When we turn on the ion pump again, pressure immediately drops. The system recovers the original pressures in a few tenths of seconds. The test shows that in case of outage, the NEG pump can keep the pressure low and it allows a quick recovery, even after days, as we can see in another experiments shown here, where the ion pump was kept off for 6 days and pressure in the -12 torr was recovered. This feature is exploited by producers of analytical equipment like microscope, surface science tools, etc., to ship the instruments under vacuum without the use of any power source, and then quickly recover the working pressure at customer site without any additional backout nor NEG reactivation. The second example shows the synergy in the Nextor pumps between the NEG element and the ion pump, in particular when pumping methane. A methane absorption test was performed with 3 different prototypes of sputter ion pumps. The pumping speed of the 3 pumps, alpha, beta and gamma, is plotted versus the absorbed quantity at constant pressure in the -4 Pascal range. This is what the total pressure gauge says. Then, if we analyze the QMS data, we realize that during the test, an important part of the atmosphere in the chamber is hydrogen. Clearly, methane is cracked in the ion pump and some hydrogen is released. Of course, the total pressure gauge cannot distinguish between methane and hydrogen, so the pumping speed measurement is greatly affected by the hydrogen released. When an ion pump works in combination with a NEG pump, hydrogen is very effectively pumped by the getter. So, if we want to know what will happen with the combination pump, we have to plot the results taking into account only the methane partial pressure. This is what we get, and it is completely different from the previous plot. This is what we mean when we talk about synergy in the Nextor pump. The synergy between the 2 elements, the getter and the ion pumps, allows us to obtain the best from both technologies. On one side, we get pumping of the species that the getter does not pump. On the other side, we can get rid of gases released by the ion pump. Of course, to fully understand it, it was necessary to use the QMS. That's all. This was the last webinar. Thank you very much for participating and we hope you enjoyed.